Now, if you're setting this up, at this point, you should be deep into solving for the time. People who understand what I said yesterday have a procedure in front of them. They see the procedure from yesterday, and that's where they should be. Our procedure was pretty straightforward. Try and find the information and put it into this kind of structure. If you have a velocity that's at an angle, you'll probably have to break it up into components. It's kind of where we left it off yesterday, but that still should be pretty straightforward. You might need to decide what's positive and what's negative. And in that structure, start thinking about what you know. Have we written anything up here that we didn't talk about yesterday? Now you should understand why I told you should be deep into solving for time. How's that look? I'm just helping out because I don't want to wait this long. I've got groups that are having trouble. I have 3 pieces of information I want to solve for the time. I've assembled it. I chose a motion equation that has those 4 things in it. So, bless you. So you guys who are dragging your feet on it, look, once you get yourself organized, we had the launch was at an angle, so you had to use a little trig. We talked about that yesterday, briefly, because our first example didn't have an angle at it, which is why I left this on the board, just in case. So my expectation was that you'd be able to just throw that in there. But it was in your notes from yesterday. Now remember, I checked. Now, you have done this before. This is not new. We've done this a couple times this year. The whole idea here is that this built on something we already did. So I don't want to spend time doing this problem. My expectation is that this part isn't the hard part. If you don't know how to do that, quadratic formula, that'll do it. Find the 2 roots, plug it into plug it into your calculator and have it plot it and find the zeros. However you want, I'm indifferent. This math is beneath me, it's probably beneath you. But I don't know what's taking so long. Because once you get the time, the problem kind of falls together. But if you don't know to do this next step, then you might, spin your wheels there too. There's no acceleration in the horizontal direction. So, this is not what I want to do today. But you clearly need some more kind of work to do this. And again, I'm not giving you a lot of practice on this, but this is pretty straightforward. This is not what I want to do today, though. So do you need another practice one? Are you stuck somewhere? Are you willing to raise your hand and say, I didn't understand how you got that? Go ahead.
So how did you get negative 0.5 and positive 2? Because when I did, I got negative 2 and positive 0.5.
That sounds like you have a sign wrong someplace. But I'll show you what I did. Did you make did you take a moment to decide what direction you're calling positive?
Yes.
And is yours match mine, or is it the opposite direction?
It is matching those.
All right, so would you agree the object landed 5 meters below where it started? So that should be negative 5.
Yes.
And would you agree it was launched upward with a velocity of 15 times sine of 30 degrees?
Yes.
And would you say gravity is pulling it downwards?
Yes.
All righty. So I have 0 equals negative 5t squared plus 7.5t plus 5.
Yes.
That's all good? How do you want to proceed from here? How did you proceed from here?
I'm trying
You factored with 2.5 and
10.
2.5 and 10.
Negative 2.5 and positive 10.
Did you divide by 5 or something?
Well, I used the line method.
I don't know what that is. So I'm going to do it my way. No, I do it your ways, but I don't know what you did, so I'm going to do it my way. Which is just to say negative 7.5 plus or minus the square root of 7.5 squared minus 4ac divided by 2a. All right. And I'm choosing an alternate method from what you did just to see how my roots work out. I actually didn't do it this way. I just plotted it and found the two roots that way. But I'm going to continue. I don't know what 7.5 squared is, but I'm sure 56.25. 4 times 5 is 20. 5 times 20 is 100. 2 negatives makes a positive. Oops. And that's still negative 7.5 plus or minus, and this is going to be negative 10. Still good? So plus 100. Take the root. I get 12.5. So negative 7.5 plus or minus 12.5 divided by negative 10, which is going to be negative 20 divided by negative 10, or 12.5 minus 7.5, 5 divided by negative 10. I don't know why your method failed you.
I found out why my method failed.
Okay.
Why?
So we're good?
Yeah, all good.
No, I mean, look, I don't want to do that, clearly. But I don't want you to feel as though I'm blowing off what your problem either.
No, I figured it out.
Right. Now, truthfully, I want you to think about it for a minute. Can I finish my thought? Math works in this way on purpose. So let's see if we can't figure out why there's two roots and what they actually mean. Okay? You'll notice that in this example, this value is positive, right? The roots would be the opposite direction, meaning I'd get negative 2 and positive 0.5 if that number were negative. The number we're talking about is the number right here, the cross portion. If that were negative, then that would reverse the roots. Because that would be that instead of going this way, the object went this way. That's what the root comes, that's where these two roots are coming from. The idea that we could have launched it downwards and not upwards. It would have just changed to the other side of the parabola. So when you look at this, I think we can all probably agree that if you're going to get 2 times and one's bigger than the other, positive or negative, if you know that one of those times is this portion of the trip and one of those times is this portion of the trip, choose the bigger time. You might have screwed up your signs, but that'll probably fix your problem. Because that's what the math is really doing. But I have another question. Yes, sir.
I was wondering, why did you put negative 5 in? Because doesn't the ball have to go up and then down? Because if you're kicking it at 50 meters going upward?
I hear your argument. But that's not what displacement means. Change in position. Where's the ball at the end? Right, we're not interested in how high the ball goes. Did I ever ask for how high the ball goes? No, I asked for how far the ball lands. And when the ball lands, it's 5 meters below where it started. I don't care about the middle. Does that make sense? Okay. Can we keep going? This is not what I want to do. Type 3 problem, right? Full deal. But now you've seen a projectile problem, a real one, all the way through. So let's talk about why a projectile problem is a challenge. It's not a challenge because it's hard. It's a challenge because there's a lot of pieces to it. Many of you did not get 26 meters. It wasn't because you were incapable. It's because you missed a small piece somewhere in the middle. Or you didn't understand the big picture of what you had to do. But even those of you who understood the big picture of what you had to do, one small move here and the number is wrong. That's a problem for you. But also, I want to be really clear that this is not an interesting question, right? It's a procedure. I can plug that into a computer, and a computer can do the procedure. I didn't ask for you to figure out something interesting. It'd be more interesting if I said, all right, I hit the ball at this angle and at this speed. Will it clear a 10-meter wall that's this distance away? That's a more interesting question. And it's a problem. I'm not just asking where something lands. I'm now asking for a condition to be met or not met. To me, that's where this transitions from being an exercise to a problem. When you're actually asked to use what you know about this. There's other things, too, we haven't really talked about yet, because we're just barely kind of cracking the surface, but I have to handle something that is going to come up, and that's what my real goal for today was. And now that you are thinking, I think, more correctly, I want you to think about this case, because this came up, and I know it's going to come up in the future. This is a type 2 problem, an artificial thing that I created yesterday, or 30 years ago, that I use over and over again. What we had just done was, this is a type 2 problem. It has a simplification. Here's what I would actually like you to do. I would like you to create an expression for how long the projectile is in the air. And in your expression, you may only have V naught, theta, and any fundamental constants that need to be used as part of your problem. So I want T equals, there'll be no number there unless the number appears organically due to a first principle. Now, if you don't understand what I'm asking you to do, I'm asking you to do what you just did. But instead of putting in numbers, you'll use these letters. Everybody understand? Now, I do want one more thing. For the acceleration, don't put in 10. Anytime you're asked to come up with an expression, use an expression for any fundamental constants as well. So in this case, the acceleration of gravity is g. That's the accepted symbol that we use for acceleration of gravity, lowercase g. Now, I'm asking you to do exactly what you just did. Make a horizontal and a vertical chart, identify the information that's been given, use whatever trig is necessary, find an expression that you can use to solve for t, and do so. But coming up with an expression is tough, and your algebra skills are being tested. The function that I think most all of you used, which makes perfectly reasonable sense, is this one. It would bring together all of the expressions and variables that we have. It's a great place to start, and most of you did. Those of you who didn't, I'm not sure why you're not doing it this way. Now, I have to bring all those things together. Every one of these things is something that we are familiar with why it got there. Is there anything there that you're not familiar with why it's there? It would have been a number if it was a problem from earlier, but we don't have numbers, so they're all there where they're supposed to be. Now, I would assume the first thing you would do here is what we've done already, factor out a t. A lot of you didn't do this, and I don't understand why, but let's just plot on, right? We still treat this like regular math. I have two factors. Each factor must be set equal to 0. So one of my answers is t equals 0. No surprise there. We asked, when is the ball on the ground? It's on the ground at t equals 0. I'm not interested in that answer. Are you? Probably not. The other one's more interesting. So, this one's more interesting. And yeah, I'm leaving out my algebra. Do algebra on your own time. I don't mean that mean. Come on. If you had 1/2 g in the denominator, that's nice, but compound fractions, your math teacher hates it. Multiply top and bottom by 2, get rid of it. You're not done. Because you understand the next thing I'm going to ask you then is, if we have this, then why can't we just eliminate t altogether? Find the range without the intermediate step of finding the time. You should be able to do that because you have an expression over here that also has time in it. If we eliminate time between these two expressions, we could have the range, the horizontal range, in terms of only the launch parameters. And do so, please. Let's shift it over a little bit so I can see over here. We have an expression for Vx. We have an expression for t. Delta x is the product of those two things. All you had to do is multiply them together. So I assume what you have is something like delta x equals 2 v naught sine theta over g times v naught cosine theta. Many of you leave it here, but you should combine like terms. This can be expressed a little bit nicer, and I would hope that you would do so. Now, do you notice here that we don't have to solve for t now? If I tell you that you kick the ball at an angle of 30 degrees at 20 meters per second, you could tell me where it lands without figuring out how long it's in the air. Plug in the angles, plug in the velocity, plug in g, and you've got where it lands. But do you also know you could do other stuff here now too? Like, I tell you I want you to hit a target 40 meters away, and you're going to use an angle of 50 degrees, and you tell me how fast to kick the ball. I could rearrange this for v naught, and now I've got an expression that tells me, how fast I need to do something to get to where I want to go. Or I tell you that this thing launches water balloons at 20 meters per second, and you want to hit something 50 meters away. What angle would you choose? Except I don't think you could do the angle question. Do you see why you couldn't do the angle question? Some of you do and some of you don't. Of course, if you were tutoring last night, you all understand. But you guys who are not thinking it all the way through, try it. Try getting theta by itself. Can you? Can you solve for theta? Can you solve for sine theta? Can you get just one trig function equals some number? You realize with sine times cosine, you're kind of got your hands tied there, don't you? And there's very little you can do unless you know some tricks. My calculus students know tricks. They should know what to do here, because they made it through pre-calc, and pre-calc taught them what to do. Now, you pre-calc kids, you're wondering what I'm talking about, but calculus kids, you know what to do, right? Every one of you? Raise your hand if you're in calculus. So you know what I'm talking about, right? What's the topic called? Trig identities. There's a trig identity that solves this. Pre-calc kids, you don't know what a trig identity is, probably. And that's to your detriment. You will learn them soon. Luckily, you don't really need them in here, but it would be nice if you had one. And because you don't know what they are, it's hard for me to convey to you what to do next. A trig identity is generally a different trig function to replace the trig function you have. Often a trig function like that is used to simplify your answer. Or in the case of this, get you past something that is impassable. We can't do something like this to solve for theta. There might be a way around it. Now, usually by this time, even the pre-calc kids have learned at least one trig identity. So kids that are in pre-calc saw this at some time. That's a trig identity. That would allow you to replace sine squared with cosine squared if you wanted, which might have some usefulness. I doubt it, but maybe. There's other trig identities that you might know, but I put this in front of a kid earlier today and they had not known it. Do you guys know this one? It's not a particularly interesting trig identity, but it says that the sine of an angle is equal to the cosine of its complement. Neither of those help us here. The one that we need here is one that probably even the calculus kids don't know or remember. And since I only have 1 minute, I'm not going to spend a lot of time on it. But I want the calculus kids to remember that I do know things. And at one time, they did too. They should know this one. And the reason they should know this one is because they learned many versions of this. A plus B, A minus B, and then cosine of the same. I know you have to leave. But if you're careful, you can use what was just written there to produce this trig identity. This one is valuable. Do you see why it's valuable? All right, bye. Have a nice day.